Thank you for joining us today to discuss the connectivity of scintillation sensors. My name is Brianna and I work in sales at Berkeley Nucleonics. We are joined by Mark Slattery, who is our Nuclear Applications Manager, and Paul Schotanus, the founder and director of Scionix. And we are excited to get started.
Okay, hello everybody. I'm Paul Schotanus at Scionix, and I'm going to talk today about some practical guidelines how to connect scintillation sensors to the outside world. And with that, I mean connecting sensors to digital bases, digitizers, and electronics, which is essential to get useful data out of your sensor. As you all know, scintillation sensors are used in a great number of disciplines, as you see there below. And each of the disciplines have their specific requirements. Well, scintillation detectors are instruments for detecting ionizing radiation via interaction with a material where light is produced. That light is converted into an electrical signal, and that carries the information in the end we want to extract. So the absorbed radiation produces a flash of light in time. And this flash of light can carry information on the flux of radiation, the energy, and sometimes even on the type of radiation by looking at the exact pulse shape. The information is usually converted into digital information, for example, the pulse height spectrum. To the left, you see there a typical radio identifier spectrum, a RID spectrum. You see some peaks. It can be a threat, it can be norm, it can be medical isotope. Or the information can be giving you information on dose. All that information is digital these days. In this presentation, I'm going to shortly tell you how you connect signals from sensors, from analog sensors, because in nature everything starts analog, of course, to digital processing electronics. What are the options? What are the things you have to be careful about? And we should all realize that very soon all processing of signals will be fully digital. And with digital electronics, I mean digital bases, for example, digitizers like you see one there at the top, or counters where you just count interactions. I'll be giving a short overview on the working principle of classic photomultiplier tubes, the most ancient type of scintillation detectors, scintillators coupled to silicon photomultipliers, and we'll go a little in detail in connectors and cable options. So let's first take a look how signals actually are generated from scintillation sensors. The most classic way is a standard photomultiplier tube around in the 1950s. The scintillator is usually surrounded by a kind of reflection material with a window, and the photons that are generated are converted into photoelectrons in the cathode of a photomultiplier tube. For the multiplier tube is a vacuum tube where we have a number of diodes. You see them there to the left. And those diodes carry an increasing voltage, so the electrons inside the tube are multiplied roughly 1 million times. You should realize that one radiation interaction produces roughly 40,000 photons per MeV, gamma rays, for example. And this, in the end, ends up with about 10,000 primary photoelectrons. And when you calculate the charge in the anode, you're roughly talking about 1 nanocoulomb. So it's a real small charge. Photomultiplier tubes are current sources, and they have a high ohmic impedance. So the current in a photomultiplier tube can roughly vary between 1 nanoamp and roughly 100 microamp. So the photocurrent is really low current. Photomultiplier tubes need voltages between roughly 500 and 2,500 volts. So we need that voltage to give the diodes each an increasing voltage to start the multiplication process in the tube. Silicon photomultipliers, on the other hand, are totally different kind of devices. They're made of arrays of micro-sized, self-quenched avalanche photodiodes operating in Geiger mode. And those pixels have a size of roughly 50 micron, and they're under a bias of roughly 25-50 volts. The principle there is totally different in that sense that one photon can hit one pixel and then the pixel fires a distinct charge. When there are more photons hitting the siphon at the same moment, the charge is larger. So there is a proportionality between the total amount of photons and the total charge pulse. So silicon photomultipliers only require much lower voltage than a regular photomultiplier. The amplification is also roughly of the order of 1,000,000 times, and they produce a charge pulse. To the right, you see a picture of a silicon PM, and all those micropixels are put together into elements of 3 by 3 or 6 by 6 millimeter, and on their turn, they are joined again to make larger area surfaces to, for example, 5 by 5 centimeter or smaller. So the signal formation in the silicon PM is a totally different process than in a vacuum tube. Of course, there are also alternative ways to detect scintillation light from materials, from crystals, or from organics. You can use pin diodes measured in current mode, like you do, for example, in luggage scanners at airports. You measure the photocurrent then. We can also measure pulses generated in pin photodiodes operating in pulse mode. They are biased with a voltage of roughly 30 to 100 volts. Or we can talk about avalanche photodiodes with an area of a few millimeter or a centimeter. There, the voltages are roughly 200 to 300 volts. We won't discuss those methods here, but I'd like to concentrate on photomultiplier tubes and silicon photomultiplier tubes. So the most traditional approach for photomultiplier tubes is using a regular voltage divider schematic like you see here in the left and the right at the top of the bottom of the page. This is a voltage divider made out of resistors, where on the one side a voltage is applied of roughly 500 to 1000 volts. You have a sequence of 50, 100, 150, and so on to give you the voltage to the different diodes. Well, those voltage dividers can be operated either positive or negative high voltage. You can do both. The big difference is that electrons don't want to swim upstream, so the cathode is always lower than the anode. Sure. When you have positive high voltage, there is a separation capacitor needed to extract the signal at the anode, like you see there to the left. With negative high voltage, the coupling out is on DC, which has an advantage for some applications. So, independent on the polarity of the high voltage, you should realize, this is trivial, but many people don't realize this, that the anode pulse is always negative, it's an electron pulse, and actually the dynode pulse, for example, on the last dynode, is positive due to the fact that the cloud of electrons goes away from the last dynode. So we have dynode pulses that are positive and anode pulses that are negative. The advantage of a positive high voltage is that you can combine the signal and the high voltage over a single connection cable, like you see in the top right. And there's an advantage, for example, from some radiation sensors like counters, where you only need one lead, one cable to operate the sensor. Positive high voltage, there is a less stringent requirement for insulation of the photomultiplier tube, because the cathode is on the inside of the glass of the PMT, and the cathode is therefore at the same potential as the glass. When we have negative high voltage, the cathode is negative, and we have to insulate the glass very carefully from the rest of the detector. Positive high voltage is the most standard way to operate a scintillation sensor, photomultiplier tube sensor, and actually that is the standard for most digital bases. The advantage of negative high voltage, on the other hand, is the absence, as I said, of the decoupling capacitor, and you can measure actually a current. You can measure the real photocurrent in nanoamps. If you have a sensitive micrometer or a current meter, you can measure the total flux of radiation by measuring the current. And you cannot do this with positive high voltage. So negative high voltage is usually chosen for applications where you want to do timing, because the capacitor gives you extra pulse in the signal. For example, for high rate applications where it makes sense to have a very clean unipolar signal. The scintillation sensor is always defined for a certain high voltage polarity. This is because the cathode is usually connected to, in positive high voltage case, the cathode is connected to ground, and also the housing is connected to ground. So if you have a detector that is defined for positive high voltage and you connect it to a negative voltage divider, the outside will be on ground, which is of course a very undesirable situation. And that's the reason that all our detectors that are operated for high voltage have a warning label for that you should only connect it to positive high voltage. Regular voltage dividers, they look like in the picture you see there in the middle. It's a cylindrical shape because the photomultiplier tube is historically cylindrical. It has a connector on them for the high voltage end of the signal, the anode signal usually. Of course, we can also have an extra dynode connection. And here you see the connectors that are most standard, SHV and BNC. For a single combined signal, anode and high voltage, sometimes another connector is chosen, which is called MHV. And this is the standard on the more older counters, and you see there at the top, bottom right. Of course, all those connectors you are using on the scintillation sensor, they should be rated for the maximum high voltage you need to operate the phototube. And of course, this should be suitable for the environment you're using your sensor. Temperature, humidity. If you use a detector underwater, then of course the whole thing should be IP68 rated. Well, the maximum voltage divider current, also called the bleeder current, is simply the maximum high voltage you need to operate the phototube divided by the resistor chain. Very simple. This current is usually of the order of 0.1 to 1 milliamp, never more than that. So your high voltage power supply should be able to produce that kind of currents. Of course, if you use a system with more than one phototube, this current is multiple of that. You should realize that there are a lot of old dosimeters around, and they can only produce quite a limited current, like for example in those portable systems you see there at the right. They're often battery operated, and that means that the current is much less than the number I mentioned there in the middle. And that means that the divider chains are usually much higher, of the order of 50 megohm to 100 megohm. And this you should really take it into account when you connect your sensor, because those devices cannot produce the current that most voltage divider actually need. Let's take a little look at the cables. There's a lot of history there, of course. The most popular connector actually for high voltage is still the SHV connector that actually is rated up to 3000 volts. For signals, we still use a BNC connector. They're quite big connectors, but they're really a proven technology. Of course, there are a lot of alternative connectors around, and there is really no particular rule which connector is standard. Of course, the cables should be rated for the voltage you're using for your particular sensor. So if you're using a detector that has to operate at 3000 volts, you should use a cable that's also rated for that. You should realize that for the multiplier tubes actually are current sources, and the cable length definitely will reduce the signal amplitude. And when you can roughly use the rule, if you use a cable up to about 5 meter length, this is still manageable. But for longer cables or noisy environments, you really need a preamplifier line driver to convert the high ohmic impedance of the photomultiplier tube to a lower value, for example, 50 ohms. For that, we have preamplifiers, which we can actually integrate with the radiation sensor in the voltage divider or in the detector itself. That actually are powered, usually with plus or minus 12 volts. And actually, we have some very simple op-amps for that, and they can drive 100 meters of cable without any problem, without losses. Traditionally, the plus or minus 12 volt in a lot of devices, in our preamplifiers, the Scionix preamplifiers, but also in a lot of other preamplifiers in the nuclear market, they are actually sourced from 9-pin sub-D connectors. And this is one of the few examples which there is actually a standard for. It's the NIM standard, where every pin of that 9-pin sub-D has a specific function. One is ground, plus or minus 12 volt, or a few for 24 and for 5 volt. This is all prescribed in some rules, but for the rest, there is no really any particular rule for cables that everybody has to follow. We commonly use actually LEMO connectors for the side for the sensor, like for example this one. It's a LEMO 0S302, which is a very good connector with a very nice sealing, high quality material. And they are coupled usually for those power supplies for cables, LEICI, which is a PVC cable, or LED11I, which is a polyurethane cable. So I said those preamplifiers can drive easily 100 meter of RG58 cable without significant losses. The output impedance of a preamplifier is positive, and that makes it actually very suitable to feed into processing electronics or digitizers, because we should realize that many digitizers are 50 ohm input impedance. And I'll repeat this a little later because it's really important. The preamplifier signals are often defined with pretty long decay times of tens of microseconds, and that is pretty historically due to requirements of classic main spectroscopic amplifiers. But for modern digitizers, actually fall times of the order of a microsecond are also perfectly adequate. Well, this is a picture of a regular plug-on preamplifier for a 14-pin scintillation sensor. You see the SHV connector and the BNC connector again. There's the LEMO connector to the left. And there's a particular pin layout there for plus or minus 12 volt, which is again not prescribed by law, but we have a choice for that. And this is how we at Scionix have defined the plus or minus 12 volt. Cable part is also indicated here. It's always essential you read the manual if you're going to make your own cables. So I said in the past, of the last many years, NIM-based systems were used, but they are actually rapidly replaced by modern digitizers. Actually, at the moment, NIM-bins amplifiers are hardly produced anymore. There you see a few examples, a few manufacturers. There are several of them around. And as I said earlier, repeat this, that the input impedance of most digitizers is 50 ohms. And it's very important you realize this, because it means that your scintillation sensor preferably also should have an output impedance of 50 ohms. So often a preamplifier is needed to connect your scintillation sensor directly to a digitizer, unless the digitizer has a built-in preamplifier, which is usually not the case. Alternatively, you can use a preamplifier resupply, which is a small box, again fed with plus or minus 12 volt, which converts the anode signal from a photomultiplier tube into a buffered 50 ohm output impedance signal. Also, high voltage modules are rapidly disappearing. We have around still the multi-channel models, and they are available. So this is also something to take into account. But alternatively, it is possible to incorporate the high voltage power supply inside the scintillation sensor, integrate it with the photomultiplier tube, so have no external cables lying around. Everything is totally sealed. In that case, we actually prefer to use a Cocker-Volton-based high voltage power supply. Here to the left to the bottom, you see the configuration. The high voltage power supply is directly plugged on the photomultiplier tube, is fed usually with either 5 or 12 volts. Takes roughly 100 milliwatt, so 8 milliamp, 12 volt. And it adds about 5 centimeters to the length of the scintillation sensor. But it totally eliminates the need for any high voltage cables and associated issues with sealing, humidity, and so on. The internal high voltage polarity for Cocker-Volton based power supplies is always negative, so we have a DC coupled output signal, which is also very convenient for high count rates. Oops, where are my slides? Oops, there we are. Another advantage of Cocker-Volton base is that it's a very good rate stability, because we are with this principle of capacitors and diodes, we can much better guarantee a constant voltage on our diodes. So at a much higher anode current, we can maintain the proper gain of a photomultiplier tube. Of course, some scintillation sensors contain multiple photomultiplier tubes, like, for example, Compton suppression shields, where you see the one at the bottom there even has, I think, 32 photomultipliers. Fortunately, we don't need 32 high voltage power supplies for that, or a 32 channel high voltage power supply, but we can simply use a distribution module where with simple gain potentiometers we can actually adjust the gain of every photomultiplier tube to the same value. Because the reality is that photomultiplier tubes never have the same gain. Because a photomultiplier tube is actually a device, like I earlier explained, where we're using secondary emission of diodes, and these gain of these devices come in wide values. And we always have to calibrate a system that contains more than one photomultiplier tube in this way. We can then connect, for example, all the high voltages together by daisy chaining. You see the yellow lines at the top, and the same for the anodes. So you can actually add all the anode signals, and you can also combine all the high voltages, so the whole system can be run with a single high voltage power supply. Of course, you should add the currents you need for the, what is it here, 8 photomultiplier tubes, so that your high voltage power supply can actually support that current. So let's go back to the 14-pin connections of still most scintillation photomultiplier tube-based scintillation detectors these days. The nice thing about digital bases is they contain a high voltage power supply, the digitizer, and actually they connect directly via an Ethernet connection or a USB cable to your computer, your laptop. There are even a few types that go wireless to your phone and have a battery pack inside, like you see the one at the top, at the bottom there to the right. Most of these digital bases actually, as I earlier said, are defined for positive high voltage, where the cathode is pin 14 and the anode is pin 11. And this is actually, again, not some kind of a law, but this is the rule that has been followed by most manufacturers for the last 50 years. But recently, there were some other pin layouts for H-stage photomultiplier tubes adopted. And actually, this has been the reason for a lot of confusion. So you have to be very careful when you buy a scintillation probe for a certain digital base. You check very carefully what the anode and what the cathode, exactly the pin numbers are, and that the data sheets, it should be documented somewhere. Because on those ones, for example, the anode is on pin 12. This is an alternative pin layout that was proposed a few years ago, but is the reason for a lot of confusion. So far about the connection of photomultiplier tube-based scintillation sensors. Of course, there's a lot more to say, but I wanted to give you a few practical guidelines here. Now let's have a look at silicon-based scintillation sensors, silicon photomultiplier-based. Well, these sensors, as said, operate with a much lower bias voltage, roughly 25, 40 volts, sometimes 60 volts. And actually, when we connect the silicon photomultiplier, like you see here in this schematic here, you can tap the signals at the cathode. They are at the cathode, yes, at the bottom, and they are actually positive, have a positive polarity, and there's a capacitor there for a little protection of the device. And there's always a load resistor present because the charge generated in those pixels has to be led to earth sometime, to ground some way. But silicon photomultipliers can also be operated at a negative bias, and this you can follow the schematic you see here to the left. And the pulses of a silicon photomultiplier can actually be made the fastest way when you actually feed them out via a capacitor. And we should realize that the rise time of silicon photomultiplier signals is much slower than classic photomultipliers. And this is simply caused by the fact that these devices have quite a large capacitance. Of course, you read in the papers that silicon photomultiplier tubes are extremely fast, but then people talk about real small elements of about 2 by 2 millimeter. But if you're reading out scintillation crystals of 1 liter, we need quite a lot of those silicon PM matrices to combine them together. And actually, the capacity then means that those devices are not fast at all anymore. Even when we terminate the signals with a low resistor value, like 50 ohm or even less, the rise times are never more than tens of nanoseconds, whereas fast photomultiplier tubes have rise times 10 times less, or 1 nanosecond. Some silicon PM manufacturers have actually the capacitor integrated on the chip, so they call this a fast output, and in this way you have directly the fast output from the SIPM module. But you can also actually use a capacitor, a series capacitor, to make the signal as fast as you can actually get out of the device. Silicon photomultiplier tube voltages are low, so the requirements actually on the voltage is much more stringent than on photomultiplier tubes. You can use all kinds of small cables, coaxial cables, even you can use small not shielded cables, because the impedance is the signals are not really fast and the signals are quite high, of the order of hundreds of millivolts. So you're not immediately punished by doing that. And of course, there are lots of possibilities in connecting silicon PMs to connecting systems. It all depends on your application and what you want to achieve. So again, interesting is that a silicon photomultiplier actually can be operated. It feels a little like a regular old-fashioned photomultiplier by applying positive bias to one part and by tapping the signal on the other side. Only the voltage, of course, is much lower. So when you change your voltage from 22 to 123 volts or 25 to 26 volts, the variation is very large in gain. So you need actually a precision DC power supply to connect to the silicon PM with a current limitation of roughly 10 milliamp. And the power supply should be a bit of a low noise, of course. You can feed the signal, the positive signal, directly into your electronics. You can even feed it directly into a digitizer if you want to, because you're not punished too much because of that, because of the slow speed of the device. And if possible, look at the signal on oscilloscope, because that gives you a lot of information on how your sensor is operating. I talk here about connections. I don't talk about principle of silicon PMs, but we should realize, of course, that silicon photomultiplier tubes can saturate rather easy, because the number of pixels on a silicon PM is limited. And if you have lots of photons, at a certain moment, all the pixels fire, and then actually it is finished. So we have to be very careful about saturation by calibrating your sensor carefully with different kind of energies, and to be sure that you are working in the right regime. And of course, the gain of silicon photomultipliers is more temperature dependent than photomultiplier tubes. But of course, there are ways to make this all more easy. You can use a so-called built-in bias generator preamplifier, which we have in our Scionix so-called new generation models. And they look like this, very short, of course, because there are no long phototubes needed. We have a small module inside that device where we generate the bias voltage for the silicon PM. It can be 25 volts, 40 volts, what is needed. We feed this with a voltage that can vary between 5 volt or 12 volt, doesn't matter. And we have a simple connector on there. One pin carries the signal and the other pin is needed for the power supply. And the body of the connector is actually the mass. As you see here, a typical signal from a silicon PM, it's if you look carefully, it's a few hundred millivolt high. That's a spectrum from cesium-662 and a high resolution scintillator, I think, or maybe even sodium iodide, I don't know. And this actually, this built-in power supply is temperature compensated in that sense that the worst temperature drift of the silicon PM is taken away, because the breakdown voltage of a silicon PM is temperature dependent. But it's a very known parameter. We can compensate for that. Of course, we don't compensate for the change in light output of the scintillation crystal. And that kind of small module provides an amplified pulse with 50 ohm output impedance. You can feed it directly into digitizers, and the gain drift, as I said, is limited to that of the scintillator. And one cable is necessary, only thing is needed to run a silicon PM device like this. And the current is less than 5 milliamps, so you can run it really with a very low power supply. Of course, there are many other options possible for cable and connectors of silicon PMs, like you see there. There's an endless amount of possibilities. In all cases, it is extremely important we should realize that there are very many ways to connect scintillation sensitive electronics, but you have to understand the physics of your sensor in order to make your choices. And there's no recipe that works for everybody because all applications are different. Thank you.
So if you are interested in similar topics like the one presented today, we created BNC Academy, which offers courses on scintillation detectors and nuclear technology. We have an affiliate program for the courses. So as you promote the classes to colleagues and friends, you will be commissioned with a sale for any sign up. Please contact us for more information.
Webinar where we would like to address the question and answers, or at least we'll address your questions with answers as best as we can. I'm not sure if this is done entirely through the question and answer chat column, or if maybe we can get an idea of how the questions will come across to us. The first question I did have, Paul, that came across earlier was why preamp signals, if preamp signals have long decay times, then that makes it, why can't they be used for, I'm sorry, I'm trying to go back to where we were. Why preamp signals that have long decay times aren't suitable for pulse shape analysis.
Well, let's click this one away first. There we go. Usually when pulses have long decay times, they also have pretty long rise times. And when you are integrating actually in a preamplifier, then there are cases where you actually integrating the information away and you don't see anymore what is hidden in the signal of the scintillator. So it depends a little on the material, and it depends also on the integration time of your preamplifier. But the fact that preamplifier pulses are usually so long, traditionally 50 microseconds, has to do with the requirements of pole zero cancellation of relatively old-fashioned spectroscopic amplifiers. I know that when we have, for example, dual mode scintillators like Click, and we have our silicon PM amplifier, which also does a little integration, we can perfectly separate neutrons and gammas. But I think the rise times of many preamplifiers are pretty large, of the order of half a microsecond sometimes, a few hundred nanoseconds. If the information is hidden in the first 50 nanoseconds, then it's difficult to extract the information because you're integrating the differences away. Anyway, that's what I think.
Okay, very good. Thank you. So also we have, that was from Dennis. Eric Lucas asks, let's see if we can, if supplying your HV, or if you can have your HV supply connected directly to the PMT, does that help with noise? I'm not sure I know the further details. To my understanding, when we connect the SHV cable, for instance, to the PMT, that is connected.
No, if you integrate the high voltage power supply with photomultiplier tube by bringing them close together, it does actually not improve your signal to noise ratio. High voltage power supplies, like the Cocker-Walton types, always have some ripple due to the fact that you generate the high voltage so close to the in a very small volume. So high voltage power supplies that are NIM bins, for example, have a huge coil inside to smooth out all the ripples, and there's simply no space for that. So if you integrate high voltage power supply with a scintillation probe, it is not a real advantage for the noise. It's just a matter that you like to have it all together to avoid any cables. Or it can be a safety application, you can seal the whole thing, but there is not really any issue with noise from high voltage supplies that's more worse due to a cable connection. No, I don't think that. No.
Okay, thank you. John Schindler asks, his understanding was that you said the Cockcroft-Walton high voltage power supplies have negative output, and that digibases typically are HVPS or positive HVPS devices.
Yeah.
So what kind of HVPS do the digibases use?
I'm not 100% sure, to be honest, but you can of course also make low noise high voltage power supplies, not by Cocker-Walton stack, but in a slightly different way. You can use, for example, also transistorized voltage dividers that also use very little current. But I'm not 100% sure about that. I only know that the Cocker-Walton bases I'm aware of, the one that we integrate with scintillation sensors, always have a negative high voltage polarity and therefore feed out DC anode signals. And on digital basis, I'm not 100% sure. So I don't have a good answer to this question. I will look into it.
Okay. And then, of course, just in general, if we're unable to answer your questions, perhaps to your satisfaction, during our session here, please feel free to send your questions directly to mark.slattery@berkeleynucleonics.com, for instance, or info@berkeleynucleonics.com. And we'll certainly see if we can find a more satisfying answer to your question if the information we provide is not quite relevant to what you're asking. Doug Hill asks, will SIPM-based detectors render PMT detectors obsolete? Boy, they've been saying that for years.
That's a good question, of course. Well, the problem, this actually is a topic for a different webinar. We have a different story once. Can silicon PMs replace photomultiplier tube? We did this a year ago, I think, or 1.5 years ago. It's still available, I think, in the library from Berkeley Nucleonics, if you want to look back to it. But should be somewhere there. But my answer is that in many applications, silicon photomultipliers will replace classic photomultiplier tubes, and are at the moment replacing it. The process has started already. But there are applications that actually silicon PMs cannot replace classic photomultiplier tubes. The simple reason that silicon PMs are more noisy than old-fashioned gas photomultiplier tubes, especially at elevated temperatures. So if you have an application where the temperature goes up to, let's say, 60 degrees or so, then the use of semiconductor silicon PM technology is much more challenging. But then it depends totally what you want to do. If you're looking at events that generate very small amounts of light, for example, if you have a classic scintillator, sodium iodide scintillator, you're looking at iodine 29 at 30 keV, and you have a seizable size of scintillator, let's say 100 cc, then my answer is that at elevated temperatures, you really have a problem with noise and you cannot see 30 keV anymore. But for other applications, it will be perfect. And of course, silicon PMs simply have an operating range up to 80 degrees C, that's it. So for all kind of oil well applications and so on, it is much more difficult. Unless, of course, you cool them, but that's more of a challenge then. So I think, yes, it will replace regular PMs for a lot of applications, but not for everything.
There will always be exceptions then.
Yeah.
We have a question from Wenzhao Is the amplitude of the signal pulse proportional to the impedance of the scope or digitizer? I'm not sure how that's being phrased. Impedance of the scope or the digitizer. Well, both.
If you connect the silicon PM signal to an oscilloscope and you push the 50 ohm button, you see what happens. It will collapse a little, but not as dramatically as a von Low-Ply tube signal, because a silicon von Low-Ply by itself has already a significant capacitance, and your roughly as a rule of thumb, your signal collapses in amplitude about a factor of 3 maybe, but you still have a lot of amplitude left over, and it becomes, of course, faster. That's a fact. So yes, the amplitude is influenced by the impedance, of course.
Okay, thank
I'm
you.
not sure that's a question, but
let's see. Mateo asks, can time over threshold technique be used for spectroscopy? I'm not sure.
Time over threshold. That's mean time over threshold. I would see that. Oh, you mean you use leading edge timing and not constant fraction timing?
That
spectroscopy, maybe time spectroscopy. I'm not sure.
Mateo, if you're able to provide a little more body to that would be helpful. We'll try to address that question in better detail. Alan asks, how does the size and shape of scintillation sensors affect their connectivity requirements?
Well, connectivity we have here defined as the way how connect your sensor to electronics. Of course, if you have a very small sensor, there is no room for lots of connectors. So if you have a very tiny sensor, like the shape of a pen, something like a pen, you have the shape of a pen like this, and you want to connect this to your electronics, then there is not much room for a connector, so then you have to use a flying leads cable with several cores. So of course, the size of your sensor influences your choice how to connect it to something else. That is obvious, I would say, yes.
Thank you very much. I'm also taking a look. Sometimes these questions are coming over the chat column. And looks like we're getting towards the end. Let me go back and look and see if we didn't already cover. We certainly welcome all of the good mornings that we've received from all over the country and all over the world. Thank you all for joining us. Let's see, basics of scintillation detectors. Oh, okay. I see. No, these actually, we've been providing some answers to some questions. Get a copy of today's slides. Absolutely, Wenjiao. The entire presentation is recorded. We'll make that available. If we have your contact information for when you register, we'll send you links to this. And the slides, I think we could probably make the slides available either in a PowerPoint or maybe even a PDF.
Well, that's perfect. I think you may want to read back the slides and look at some of the connection schemes. It may be very useful for some people. Yeah.
Absolutely, yes, we will make those available to you. It's a good question. Thanks, Wenjiao. Gamal, I hope I'm pronouncing that correct. I'm sorry. He's wondering why. Well, he thinks we should give these webinars more often. So, I think we should too. Given time and resources for putting these together, we certainly can do what we can. We don't provide only, or the webinars are not only about radiation detection, for instance, and other radiation topics. We do also put together webinars for our test and measurement products, for our radio frequency and microwave products as well. I we didn't really go over an introduction earlier as far as some of the different things that we do cover at BNC. And all of these topics, all of the different product lines that we manage are covered in webinars. So always maybe check our BNC website at berkeleynucleonics.com. That's berkeleynucleonics.com. And we'll typically always have some sort of a updated schedule of upcoming webinars. So we do invite you to check those out as well.
There's still a question there that's interesting, Mark.
Let's see, I'm interested in random metrology.
No, the other one, for feeding a click detector signal into a digitizer, do we need an external amplifier? No.
We shouldn't.
You can feed a signal directly into a digitizer.
Should be able to.
That's fine.
Although I must maybe we want to mention that most digitizers do have a 50 ohm input.
Yeah, that's okay. In this particular case, it's fine. That's
okay.
for spill shape analysis, that's no problem.
Okay, so preamp is not necessarily a requirement. Gamal is interested in radiation metrology as per NIST. So Gamal, we invite you to contact us, or you can contact us through info@berkeleynucleonics.com. But please, if you have questions pertaining to a more specific topic, we invite you to give us a shot. Give us a shout. The value, Wenjiao's, good questions. What's the value of typical quenching resistor in SIPM?
Yeah, I think it's in the schematic. I think it's 300 kilo.
Okay.
100 to 300 kilo. You need to have a certain. You need to lead the charge away to ground. I think it's a few hundred kilo. I think it's in one of the slides. You can look at the manual from manufacturers like Hamamatsu or in Semi, but I'm pretty sure it's 300K.
Okay. Interesting question from Huang Li. What's all the fuss about strontium iodide? I'm not sure.
It's outside the scope of the webinar, but
true.
Iodide is a high-resolution scintillator. It has nothing to do with particular questions we addressed here, but it's a high-resolution scintillator, and you would go to the webinar which we gave, which is called Myth and Reality on High-Resolution Scintillation Materials. Maybe you should check that one out. It should be also in the library somewhere.
Okay.
The material is addressed out there someplace.
I think so. As far as the ability to use PMTs, use SIPM, there's no restrictions. That's certainly all stuff that's available for strontium iodide. Blah 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 blah.
Interesting question. The future of connectivity: Wi-Fi or Bluetooth? A lot of sensors already work with Bluetooth these days. Yeah.
Well, it's interesting. I mean, Wi-Fi and Bluetooth has certainly been useful.
There are also different protocols for communication between sensors, and but there are definitely sensors already working with Bluetooth.
So I would imagine, though, perhaps the question there is maybe, are we talking about between the detector and the MCA?
Yeah.
Or are we talking, I mean, the other option is digital bases that are attached to the PMTs. And if the information from the digital bases can be transmitted via Wi-Fi or Bluetooth rather than through Ethernet or USB connection, there are people that are working on that.
Yep.
We don't have one for you yet, but I have heard of ideas. People have called and described using local transmitters from a stationary PMT with say like the BMCA or the Ortec Digibase, some other type of device, and transmit wirelessly to a laptop or a PC.
Well, the question is also how sensitive is it for interference? Ethernet connections are of course used for communication between computers and so on. And a lot of bases these days work with Ethernet, and there's a lot of flexibility there in connecting multiple sensors to one network.
Okay.
So I think Ethernet is at the moment more getting the more common standard for communication between digital processing electronics and the networks.
Okay, that's good insight. Doug's wondering about, both, I guess, at this point, I would say that is more of a development question for the analyzer developers, not so much for the detector developers. But that's a very good question that we here at BNC will certainly propose and indicate that there's increasing interest in wireless exchange of data between the detectors and the analyzers. Thank you.
Yeah.
Let's see. Environmental nuclear engineering is very much into Internet of Things radiation detectors. Okay, now that is obviously network, but is that necessarily Wi-Fi, or is that Ethernet? I know you mentioned Ethernet, certainly, but I would assume then that internet or the it's a good question. That's certainly something I don't have an answer on, something out of really the scope of this, but that's a great idea for future webinars, something for us to propose and present in the future. Wen Zhao, last question. He says, is it better to choose a higher impedance or low impedance scope for the measurement of a SIPM's output?
Well, if you're just examining your signals, it doesn't really matter if you terminate the signal with 1 megohm or with 50 ohm. As long as if you're using 1 megohm, of course, you should be able. You see more amplitude. Your signal amplitude is much higher. With 50 ohm or even lower termination of your SIPM signal, you see the real speed of your sensor, the maximum you can get out of it. So it's not really, you're talking about measurements. Yeah, well, I don't think really it depends what you want to do with your signals. If you want to get fast signals out of your SIPM detector, you need anyway an amplifier chain with a low resistor value in order to get the minimum rise time. All right, I mentioned minimum rise time of a SIPM of, let's say, 1 square centimeter is roughly a few tens of nanoseconds. So it depends on your application.
Okay. And looking at the time here, we are probably getting close to the top of the hour, but we do have contact information for you here if we were unable to get to your questions. If you want to follow up, if you want to offer ideas, please, by all means, use any of these contacts via phone, via email to send us your questions. Huang Li's wondering if there's any trade shows we'll be attending in the U.S. or the EU.
SORMA conference in Michigan in 1 month.
Ann Arbor, Michigan.
Yeah,
there will be that.
Over a month, 5 weeks from now.
About 5 weeks from now, the SORMA in Ann Arbor, Michigan. IEEE will be in Vancouver, Canada, British Columbia this year, and BNC and Scionix will be attending that. So we would certainly look forward to meeting you then. Wen Zhao did have another question. The noise level, is noise level also proportional to the impedance?
No. Noise level is not influenced by the impedance you terminate your SIPM to. Noise level is a function of temperature and, of course, the number of SIPMs you are actually connecting to your scintillation material you use. The total surface area of the SIPMs you're using is influencing your noise level, and the temperature is the most important parameter.
Very good. Well, we're at the end of today's presentation, and we hope that the information has been relevant to your individual interests and projects. And I want to thank Paul Schotanus and Brianna Thomas for their invaluable contributions today. I also want to thank Jordan Malakaman in the studio. He's been coordinating a lot of this stuff behind the scenes. I want to thank Jordan for the great job that he's been doing. And of course, I want to thank all of you for joining and watching today, or at least those of you that are still with us, watching us now.
Yes.
Thank you very much.
Thank you very much for your time.
Of course. I'm Mark Slattery. We hope that you'll see us again. Bye now.
Thank you. Bye.